Thank you. Can you hear me all right in the back? Everyone? Okay, perfect. Well, before starting with all the technical stuff, I want to make use of a really old legend from Mexico. In the beginning of time, when humankind was new to the world, everything was cold because humankind did not know fire, did not have a way to warm themselves. So people had to eat raw seeds. They had no way to cook them. And the elders in the village sat down to think, this cannot go on. We cannot keep eating raw foods and being cold all the time. So who will go to the abode of the gods and bring fire back to us? And some of the bravest warriors had tried doing that and failed. And they sent the donkey to do that, and the donkey had failed because every time he tried to catch the sun behind the next mountain and the next mountain, the sun was always hiding behind a mountain further back. And they didn't know what to do until the tlacuache, the opossum, was sitting in his little wooden cage. And the opossum said, I will do it. Let me out of my cage, and I will bring fire back to you from the gods. And the elders told the tlacuache, are you sure? You are so small and so fragile. And tlacuache said, yes, I am not afraid of death. Let me free, and I will do it for you. So they let him free, and tlacuache started his long journey to the place where the gods lived. And he walked for days and days to the east, trying to reach the sun. And on the third day, he reached the moon at nighttime. And he started talking to the goddess of the moon. And the moon told him, what are you doing here, little tlacuache? And tlacuache said, well, goddess moon, I am trying to reach the place where the gods live to get fire from them for humankind. And the goddess of the moon said, I have some beef with the god of the sun. He banished me to the night and the darkness. So I'm going to help you, little tlacuache. So the goddess moon cried, and when she cried, her tears hit the ground, and out of the ground sprang up some nourishing plants that the tlacuache could eat and carry on his journey. So he carried on his journey, and on the fifth day, little tlacuache reached the place where the gods lived. He reached the abode of the god of fire and the god of the sun. And he saw that the old god of the sun and fire was sitting in his cave by a fire on the ground. And the old god of fire said, who is there? And little tlacuache said, it's me. It's just a tlacuache. I'm just a messenger from humankind. Please, god of fire, please don't harm me. I just request that you let me pass the night here, and I will do you no harm. And the god of fire said, okay, you may sleep here, but don't touch anything. So little tlacuache made as if he was asleep. And eventually, little tlacuache heard that the god of fire himself was asleep. So he stood up quietly and went to the fire and grabbed a blazing piece of charcoal, and grabbed it with his tail, and wrapped his tail around the blazing fire and started running back to the place where humans lived. Right? And he ran and ran and ran. And then he saw behind him, and there was this wall of rocks and fire crashing down of him, because the god of fire is also the god of the volcanoes. And he was chasing, the evil god of fire and the sun was chasing poor little tlacuache as he ran with the blazing charcoal wrapped under his tail. And little Tlacuache eventually leaped, and the god of fire grabbed him and threw him far, far away, being sure that that would kill the poor little Tlacuache. But poor little Tlacuache was stronger than that. And he eventually reached the place where humans lived and gave them the blazing piece of charcoal. And the elders in the village said, "Oh, Tlacuache succeeded. He brought fire back to us." So eventually they nourished him and cured his wounds and cured his poor little burnt tail. And that's how humankind was able to obtain fire, because the little Tlacuache brought it for them from the gods. And this is the story of why Tlacuaches don't have hair on their tails. It's the traditional Mexican story of why the Tlacuache doesn't have hair on their tails. So Tlacuache is the Mexican Prometheus, right? Bringing fire from the gods. You will see why this is relevant to evolution in a second. Evolution is a really old program. Even before we started writing evolution back in the 2000s or late 99, the very first calendar application we wrote for GNOME, we did it in 2 weeks. When Miguel and Arturo and myself were back in university, we said, we're going to write a calendar program in 2 weeks, right? Because back then, there was a budding standard called vCalendar. So Miguel wrote a parser for vCalendar. I wrote the GUI using GTK, and Arturo started writing some of the week and year views for the calendar. And Arturo had already worked on a contacts program called GNOME Contacts or something like that. And it used another new standard back then, which was called vCard, which is still used to these days. Some people had written 1 or 2 random email readers for GNOME. This is what the first version of GNOME Calendar looked like. You can see, this is GTK1, right? You can see all the motif-like bevels, our first set of icons. We didn't have symbolic icons back then. This was the first GTK calendar widget. This was a GTK lists something. This was a custom widget we wrote for the calendar. It was very, very basic. This is Balsa, one of the first GNOME email readers. Again, this is GTK1. We had our original icon set down there. It was really simple, didn't work very well, but you know. Some friends started a company called Helix Code, which later got renamed to Ximian. And that's where we wanted to write a new groupware suite, because groupware was the big thing back then in the early 2000s. Customers had told us that one of the big reasons why they couldn't move from Windows to Linux was because they needed Outlook. So we set ourselves a mission to clone Microsoft Outlook. And that's why you see evolution, and it looks exactly like Outlook looked back in the 2000s. We rewrote the calendar and the address book from scratch for copyright reasons, because Helix Code wanted to own the copyright for that. But it was still GPL software, so not much of a problem there. vCalendar had been phased out by then. There was a new standard called iCalendar that's still in the RFCs that they are still used to these days. vCard is still around. People at the company started writing a new email client based on a library called Camel. And Camel was itself based on the Java Mail APIs, which were fairly good and fairly comprehensive back then. And we were very, very keen on having syncing with Palm devices. The Palm devices were these things. Before smartphones, there were these devices called the personal digital assistants, PDAs. They were fantastic. They did not connect to the internet. You had your calendar, your to-do list, your appointments, no distractions, a few snake games and Tetris. They were great. And every business person wanted one of these and carried it in their pocket. And it was very important to be able to sync your calendar on this thing with your calendar on the computer. So there was a lot of effort put into evolution to do that. And sadly, these are no longer around. Smartphones appeared in the mid, 2000s. So we moved on to that. Development was very different back then. The concept of continuous integration, the concept of building your code after every change to see if it still worked, was new back then. It was basically invented at Mozilla by Tara Hernandez. She wrote one of the first CI systems in existence called Tinderbox. Mozilla had the problem that they had to build the Netscape. Well, it was not Mozilla back then, it was called Netscape. Netscape had the problem that they had to build their browser code base for Windows, Linux, Solaris, IRIX, Mac OS, for many, many platforms, and things were breaking all the time, and they needed a way to ensure that the build was always working. So Tara wrote Tinderbox, and over time it became a platform not just for doing builds, but for integrating development tools. So Bonsai was a tool for navigating source code repositories. LXR was a tool for navigating your source code based on, you could click on a function name in the source code and it would take you where the function was defined. So it was a tool for navigating very big code bases more easily. The only revision control system we had back then was CVS, which is really terrible. It was really primitive. And we were using the early versions of auto tools for GNOME and Evolution. So you can imagine just how terrible all that was. And a typical day in development was you would update your source code from upstream. So you ran CVS update. But you might want, CVS let you update individual subdirectories, not the whole source tree, like we're doing with Git nowadays. And since things were always breaking because we didn't have a way to ensure that the code always compiled, it was very common for people to start their workday just by updating the calendar source code, or just the address book source code, or just the mailer source code, trying to build just that little subdirectory, install the new libraries, and see if they could still get it working, because everything was breaking all the time. GNOME was breaking its APIs all the time. We didn't have stable APIs or anything. And Tlacuache brought fire from the gods to humankind, and we thought, or I thought, being the Mexican in the team, I thought that we were bringing Outlook to mere mortals, right? So we wanted to, or I wanted, Miguel and I wanted to have a code name for the data storage part of Evolution, call it Tlacuache. But the English speakers in the team, told us that the word Tlacuache was too hard to pronounce. English speakers saying about things being hard to pronounce. And they wanted to call it another animal name. And we had a very colorful Australian in the team, so we ended up naming things in Evolution after Australian animals. You'll see that in a second. And now let's move on to what I really want to talk about. Evolution is a really old source base. Evolution Data Server is the part that people are mostly interested in nowadays because it's still used for the new applications, GNOME Calendar, the system-wide contacts, the system-wide accounts. And Evolution Data Server is in this unfortunate place where many of our old infrastructure libraries that are written in C all stand. And they all come from the time before we had CI. They come from the time before we had source code sanitizers. They come from the time before we had really nice tools for keeping large source spaces in check. So the first task I'm doing is to add the basic toys to Evolution's CI, which up until recently was very, very basic. It just built the thing and ran the test suite, and that's all it did. So let's look into these things. This might be old news for long-time maintainers, but my purpose behind this talk is to show newcomers that these tools exist, how they can be used, and maybe you can learn a thing or two about why there's so much previous work to be done before we modernize the source code. This is a test coverage report for Evolution Data Server. A test coverage tool, what it does is it runs your test suite and tells you exactly which lines of the source code got executed and which lines did not get run at all. So very, very high source code, which has a very, very high requirements for reliability, empirically is seen to have over 90-something% coverage in the test suites. That means that when the test suite runs, over 95% of the source code gets exercised by the test suite. Evolution Data Server is not in that good position yet. Some of the source files are not tested at all. Some are only partially tested. So we have some work to do there. This is in contrast to other code bases which also have test coverage. The left, we have the test coverage report for glib. Glib is fairly good. It's at 80-something%. librsvg is at slightly better. It's almost 90%. And this is not to gloat about the state of librsvg, but it happens to be code that is much easier to test. You know, librsvg just takes SVG files and renders them into pixel data. So it's very easy for this thing to have SVG files which exercise the library, and we compare the output PNGs to reference data. So it does no input-output, it doesn't depend on the network, it doesn't connect to any services. So there's not much that is hard to test there. However, in glib, things are harder. In glib, testing the GI repository compiler, which has very, very little coverage, is harder because to do a lot more previous work to be able to exercise all that source code. If you want to exercise all the I/O paths in there, you need to do a lot of work. And that's also the case for Evolution Data Server. You know, how do you test connection to a Microsoft Exchange server in the test suite? Do you spin up Microsoft Exchange in your CI? That's really hard to do. So it doesn't do that. So we need to find ways to decouple the algorithmic code from the code that is hard to test. So a test coverage report tells you what code gets executed when you run the program or when you run the test suite. You can do different things with this. Once you drill down in the coverage report, this is what you will see. This is one of the source files in Evolution. And the test coverage report tells you the lines that got executed are in green, and it tells you the number of times. You can use that as a cheap profiler. The lines that are yellow have branches in them, decisions. And the lines that are yellow means that one of the conditions was tested, but not the other one. For example, in this line 153, It's yellow, and it means that the statement, if not file, that always evaluated to false, and the code went through to the next line. It means that the go to error, malform, blah, 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 which is in red, that line never got executed because that condition never jumped inside the if statement. So if we wanted to test the go to error, malform URI code path, we would need to set up a condition so that the if not file is true, and it would jump to the other case. Likewise, we have no test case where a file has, I don't know, an invalid URI or something. So the temp file is always able to be created. So this code, these 2 lines of code are never being tested. So we have to make a decision. Do we want to test them? Do we need to test them? Do we need to test that error propagation works correctly? In that case, things to think about. Branch coverage is the thing that tells you which of the branches were taken and which were not. So you can make a decision about whether you need to have finer grained data in your tests to see which ones execute and which ones didn't. So over there, it means that maybe priv is dirty was true sometimes and false sometimes, and writable was true sometimes, false not other times. So we see here that we did go into the if statement because the lines inside got executed, but we didn't test all the combinations of those, of the is dirty and the writable flags, right? So what can you use test coverage for? You can use it for multiple things. If you are new to a code base and you don't know where anything is implemented, but you can actually run the program by hand and click on its controls and everything, you can build the source code with test coverage running, with a coverage report running. You can run the program, click on things, run a feature, look at the coverage report, and the lines that are green will tell you where your functions are implemented from the user interface. So that's one way you can use it. The other ones, which is the one I just showed you, is test coverage. Which of my code gets run by the test suite and which one is missing tests? You can use it to determine the comprehensiveness of your test suite. If you have different compile time configurations, for example, are you building for Linux? Are you building for Windows? Are you building for BSD? Is there some if-def that only happens with a certain build time configuration? Are you enabling debug code in if-defs? Are you disabling them? Are you trying some optimizations gated by compile time options? If you want to ensure that some of those compile time configurations actually work, you can ask the coverage report to tell you if those lines got executed or not. For example, in librsvg, it builds for Windows. It makes its best effort to run correctly on Windows. But I have no way of ensuring that myself. So I just let the CA run on the Windows runner, and the coverage report tells me which of the Windows-specific code got executed, and I have to make a decision. Can I fix this? Is this like purely algorithmic code that only runs on Windows that I want to test or not? So it lets me make that kind of decision. We already talked about this. Which compile configurations you want to test? You can make decisions. Can you set up virtual machines or other ways of running your code in other platforms? Can you set up CI runners for things you actually want to test? What code do you think you are sure that gets run by users when they are going through your program versus what gets run in test suite? Do you want to be able to drill down into other parts of the code that you are not sure if the users are testing or not? And the thing that always happens when you first set up a coverage report is you start finding algorithmic code that should be easy to test because it's just there. It depends on no I/O, no network, nothing, but it's not being tested. So you say, oh, I can add a test easily for this. So you go and do that and improve your test coverage. Then you figure out that some other code is not being run because it depends on networking, I/O, external services. So you have to make decisions. Do you set up a mock service so you can test your code? Do you set up mock data to feed into your program? Do you simulate I/O errors somehow to test your error paths? Do you want to make some error paths are absolutely correct and well tested? Are some others just supposed to generate an error message which you basically ignore most of the time? So it lets you make that kind of decision. I was telling you that we had a very colorful Australian programmer in the team, one of the authors of the mailer part of evolution. So we started naming the components in evolution after Australian animals. So instead of tlacuache, we had a wombat, which is not hard to pronounce at all, right? But wombats are really cute. Anyway, so that's not a bad change. Trivia point: wombats, when they poop squares. They poop little cubes so that it doesn't roll down wherever they do their thing, and other wombats can find each other. It's really strange, but it's the only animal that poops little cubes. Anyway, address sanitizers. The next thing I added to Evolution's data servers CI was a pass with ASAN, address sanitizer. This is absolutely vital for C programs, because C is a memory unsafe language. It means that you can have invalid pointer dereferences, null pointer dereferences. You can have out-of-bounds accesses to buffers, which are really dangerous for attackers. Use after free. All the memory unsafe things that we know C lets us do very easily. The address sanitizer feature can help us find that. Using it is really easy. You just compile with those C flags, and it lets the compiler instrument your code. It lets the compiler add extra checking to your source code so that when you run the program, it will tell you if you made a memory safety error or not. It replaces malloc and free in the runtime so that they get checked versions and tell you about errors. The important thing about sanitizers is that they are runtime things. Your code needs to run for address sanitizer to be able to find errors in it, because it's doing checkings at runtime all the time. So if you look into your coverage report and find a big section that is not being run, address sanitizer is not telling you about any potential errors in there. This is another reason why having a coverage report is useful, because you will know which parts the sanitizers are able to reach or not. So this is a fairly complicated error handling chunk of code, but it's not being run at all. So we don't know if it has memory safety bugs or not, right? There's another sanitized for undefined behavior, like when you in C, whether it's valid to shift a value left or right, a numeric value left or right depends on the sidedness of the value. So UBSAN will tell you if you are doing that wrong. C doesn't let you catch integer overflow easily, so you have to run it through a sanitizer. Attackers loved integer overflow to construct exploits. C doesn't tell you when float to int conversions overflow, so sanitizers help you catch that. One of the other parts of evolution is Camel. Camel is the mail library. It's the library that parses emails, connects to email servers, IMAP, POP, that sort of thing. And it's called Camel because camels, just like the library, is able to go through very long distances without food or water. The other toy we have in CI is a static analysis pass. Static analysis happens at compilation time. Your code does not need to run, but static analysis can catch many errors for you. So, for example, it will tell you of some unused code. This is all CMake stuff, but for example, up there it says API argument with non-null attribute pass null, so that's definitely an error. It means that in some parts of the source code, one function is annotated to say this function must get non-null parameters, but it's being fed a null. So it tells you exactly in which conditions that happens. Down here, it detected a memory leak because it saw that you didn't free something that you just allocated. Stream handling error means that usually in C, you forgot to check an error before calling an IO function. Or after calling an IO function. So for example, this is one of the stream errors. The static analyzer looks at your source code at compile time, and it tells you, okay, if the code gets to this point, and we call on line 1308 there, and we run fgetC, we're getting the result of fgetC, but not checking for errors. So it tells you, oh, here the position in the file might be undefined if you forgot to check for errors, so you need to do that to do it correctly, right? So why do we go through all this trouble before starting to fix the source code? Because this is infrastructure code. We have many infrastructure libraries that are written in C from years and years ago, before all these tools became generally available. And we need to keep infrastructure running and make it as correct as possible. The C language does not make that hard at all. We've been thinking of renaming it to the CVE programming language. So these are tools that help you clean up a code base, you know. We all know that untested code means broken code, so if you want to flip it around, you'll remember your discrete math way of flipping that around. It means that working code implies tested code. So you can do manual tests. We had QA teams back in the day, and we paid those people to run all the functions in the UI trying to exercise the code. But nowadays, we know it's much cheaper to have a test suite that you run on every commit. But how do you know what's being tested and what isn't? You run a coverage report, you run an analyzer, a sanitizer. And curiously, even though we have Australian animal names in evolution, we don't have any koalas, we don't have any kiwis, we don't have any kangaroos. And I just realized that it was not intentional that we don't have any animals that start with K. So, something to think about. And that's all I have. Thank you.
Thanks, Federico. Question for you. Most of these things that you pointed out are for legacy C code bases, for the profilers and the analyzers and things. With librsvg, do you have equivalent Rust? I mean, you obviously don't need memory analyzers because it's a memory-safe language, but do you have equivalent profilers and analyzers that you run on that test suite?
Is your question if these sort of analyzers are present in Rust code? Or?
Yes. Yeah, are there equivalent, you know?
Yes. In Rust source code bases like librsvg, if you're using the safe subset of Rust, it guarantees that you will have no memory safety errors, so you don't need something like ASAN there, because those kinds of bugs cannot happen there. There's no null pointers, there's no invalid pointers. The programming language does not let you reach a state in you can dereference an invalid pointer, right? You can get those if you're using the unsafe part of Rust, and there's checking tools for that. There's a tool called Miri, which is, well, it's a compiler thing. It runs your code through special analysis to see if all the combinations let you reach an invalid pointer, things like that. So there's tools for checking that in unsafe Rust. But the nice thing there is that Rust code bases have usually very small chunks of unsafe Rust within them. So most of the source code is safe, and you have these little chunks of unsafety, which is where you really need to pay attention. But you don't need to pay attention to all the source code, which is what you need to do in C. You need to run carefully through every line, right? And for static analysis, the Rust compiler does a lot of static analysis all the time. That's how it does the borrow checking. That's how it tells you this condition should not be reachable at compile time. So it tells you, it's able to tell you a lot of that. And the people who are doing work for high reliability Rust, like the people who are trying to get Rust validated for aerospace and that sort of thing, they have special tooling to check your code even harder, basically. Thank you.